The recording. Yeah. We set up that we get this together. So perfect. Okay. So just go ahead and start. Yeah. So hello everyone. I'm Connor Sullivan. I'm going to give a tutorial on FireSim, which is a architecture research tool that we use in our lab. So who am I? I'm a PhD student here at the University of Kansas. I work under Professor Heechul Yoon, and my research is focused on computer architecture for real-time systems. So this tutorial, as I said, is going to be an overview of a computer architecture simulator known as FireSim. This is a tool created by the UC Berkeley Architecture Research Group. This is a QR code. If you want to scan it, it should take you to the FireSim website. If this QR code doesn't work, you can just go to fires.im. It should get you there. So my relation to this tool, I did not make this tool. This is, again, something created by UC Berkeley, but I use it every day for my research. In fact, we've published one paper that heavily utilizes FireSim for implementation and evaluation. So just as a general agenda of what we're going to be talking about today, I'm going to give a little bit of a background on simulators, just for people who don't know, talk about some details of FireSim, how we use the tool in our lab, talk about this other thing called Chipyard, then kind of give an overview of how you can configure FireSim to do what you need to do, and then go into a live demo portion actually using FireSim. So we need architecture simulators because in research, we need to change things and run experiments. In software, this is easy, in air quotes. Obviously, it's not easy, but it's easy to change things. But you can't modify a processor architecture that's in your computer. You need ways to change this, and so that's why we have architecture simulators, so we can test new ideas for processors, essentially. So there's a couple terminology things that I'm going to go over here. So there's different types of simulators. And these two figures here. On the left, we have what's known as a functional simulator. All it's going to do is just emulate the functional correctness of your system. So it's just simulating the ISA or instruction set architecture. You're just running instructions, updating some register files, have a little bit of a memory simulation, but there's not really cycles. It's not directly relatable to hardware. On the right here, we have a picture that is a cycle accurate sim, which basically gives you complete high fidelity microarchitecture detail and timing. So you can see in this picture on the right, we have the branch predictor, we have caches, we have this out of order pipeline, we have a more detailed memory model. So you get more fidelity on the right than you do on the left. Now, of course, we also want to talk about running an OS in this simulation because any real system is going to be running an OS typically. There's two approaches to this. So on the left, we have what's known as a user level simulation. Basically, the simulation itself doesn't actually run an OS on it. It's just going to be calling out to the host OS of the system that the simulation is running. This can be a bit faster, but again, you have less accuracy. It's not as high fidelity. On the right, we have a full system simulation, which that's where you're actually running a real OS on top of your simulated hardware. So you basically have an actual system running at all times, and that's going to give you the highest fidelity. So quickly, an example that isn't FireSim, so we can kind of have a reference point to why you would want to use FireSim. So Gem 5 is another popular simulator in the architecture community. It's kind of known as cycle almost accurate in the sense that it's basically cycle accurate, but it's not real hardware, so it's not going to be exactly the same as if you actually designed and taped out the chip. But it does allow for full system simulation, so you get very high fidelity. The big downside to it is it's a software-based simulator, so you get C++ models. Everyone knows C++, it's easy to use, but it runs at a rate of kilohertz, so it can take days to do evaluation. So what about FireSim? Well, FireSim is also cycle accurate, more accurate than Gem 5. FireSim is also a full system simulator, so we can actually run an OS on the simulation. And the big difference is FireSim is FPGA accelerated. I'm not going to talk too much about the details of what that actually means, but what that nets you is you get to use real hardware. So we're writing real RTL, putting it on the FPGA essentially, and we're running it at tens to hundreds of megahertz. So orders of magnitude faster than Gem 5 while being even a little bit more accurate and more relatable to real hardware. So talking about that hardware, in FireSim, our hardware models are real RTL. We're writing real RTL code. For FireSim, we're using a language called Chisel, which basically just produces Verilog. At the end of the day, everyone probably knows what Verilog is, and that's synthesized with Vivato and then put on the FPGA. Gem 5, on the other hand, as I said, you're writing C++ models with a bunch of complex scheduling in the background to mimic a real processor. So these models are accurate, but FireSim itself, once you've written this, you've simulated it, you can actually then tape it out, and actually get a real chip back. So is FireSim always better than Gem 5? No, not really. There are trade-offs you have to consider. First of all, dealing with RTL can be overly complex at times. You have an entire SoC in front of you when you are trying to make changes to FireSim. That's a lot to work with. And prototyping in FireSim, because of this, is in my experience a lot slower than in Gem 5. One of the problems here is long build times. So if you change something in FireSim, you need to simulate it. You have to build it first, and that can take 4 hours. So you change one thing, you test it, 4 hours later, it's broken. You have to do that whole process again. Whereas in Gem 5, it's C++, it compiles quickly, and you can just kind of iterate a lot more efficiently. Gem 5 is also more mature. It's been around for longer. It has more support, more thorough documentation, more people use it. FireSim is a little less used. And then along with that, no one knows this mysterious thing I've been talking about, Chisel. I'm sure no one here has heard of it, but most everyone knows C++ in some capacity. So what even is Chisel? Well, Chisel is a Scala library and compiler plugin. That's how they describe it on their website. And Scala is basically just a language that's based on Java. So it's just an embedded language in Scala. And you're basically just writing object-oriented and functional RTL code that when it's run, it produces Verilog that you can synthesize. You get the upsides of a more modern language, but again, there's a learning curve. No one knows Chisel. No one really knows Scala most of the time. So you have to learn a lot to get this up and running. So with these difficulties, why would you even want to use FireSim? Well, I mean, the big point here is the simulation speed. Kilohertz versus megahertz, orders of magnitude difference. For example, in FireSim, I can run a spec workload in 4 hours, which sounds slow, but if you want to do that in Gem 5, it's going to take you days or even an entire week to run a single spec workload. So when it comes to evaluation, you're able to move a lot quicker with FireSim. Along with that, with FireSim, everything is real hardware. You could do something in FireSim, simulate it, test it, go through some processes, and it could end up as a real processor chip. So it's when you're doing research with FireSim, it's more directly relatable to something in the real world. Whereas Gem 5, it's just C++ models. Sometimes it might work in Gem 5, but it might not actually be feasible in real hardware. FireSim gets you that connection. And then along with that, there's another point that I'll go into a bit more here. With FireSim, since it's real hardware, you can do accurate power and area analysis of your designs. And to do that, you're going to use another Berkeley tool called Hammer. And basically, this just allows you to take your RTL that you're simulating, lay it out as an entire SoC and see the area, and then look at also the power consumption of the individual components that you're adding in. We've done this, a previous paper in our lab did this. So basically what this is here is an actual chip laid out. These big giant blobs are the processor cores. And then down here, very small circled in red is the component that we implemented. So you can actually see how much space everything takes up if you were to actually take this out. And so if you have some sort of design, say it gives you a 4x performance improvement or whatever, then you can say, oh, and it also only costs 2% of the area and 0.2% of the power overhead. So it strengthens your evaluation and strengthens the relation of your design to real hardware. So now we're going to get into some details more of what FireSim really is and how you can use it. Just a quick note about the version that I'm talking about. So the version I'm using every day is 1.17.1. There are newer versions. I just haven't updated to newer versions yet. Everything should be pretty much the same, but there might be some slight differences, just to take note of that. So as a bird's eye view of what a FireSim simulation system looks like, this is from their documentation. So you're going to have this manager instance, which is going to be the machine with FireSim actually on it. And then you'll have your build farms, which basically these are either the same machine or some other machine. That's where you do your bitstream generation. So you've written your chisel code, then you can hand it to these build farms, and then they're going to output Verilog, which goes through vibrato synthesis. And then you can take those bit streams that you get back and put them on the run farm, where that's where you're going to have your FPGAs. That's where the simulations are going to be hosted. And so you kind of have this distributed environment. It could all be one machine, but it could also be multiple machines in any configuration. So to do this, FireSim was originally designed for use in the AWS cloud, basically allowing you to scale out your simulation pretty much infinitely. The original FireSim paper was actually written to simulate an entire data center all at the same time, like a 1024 node data center all at once in the cloud. Of course, that's expensive. So as of December 2023, we were actually able to, they implemented local FPGA support, so we can do this locally without using AWS. And using both of these in conjunction offers a nice flow. So AWS obviously costs for daily use, but it's more scalable in the sense that you can just get as many FPGAs as you need. If you have an FPGA locally to use, though, it doesn't cost daily. And so you can iterate locally. And then when you need to scale out, because FPGAs aren't cheap, go ahead and use AWS and do your evaluation there. And so how we actually use it in our lab, so we do just that. So we use both AWS and a local FPGA setup. So this is a picture of literally my desk with the FPGA on it, which was a Xilinx VC118 FPGA. We use this daily for prototyping and iterating our designs. And then when we're getting into crunch time, when we need to collect a bunch of data, we go up and spin up a bunch of AWS instances and run all our simulations in parallel for quick data collection. So there's this other thing that I haven't really mentioned yet, but it exists under FireSim, but when you talk about FireSim, you're also talking about this thing called Chipyard, essentially. It's another UC Berkeley tool, so thank you, UC Berkeley, for all these tools. And basically all this is it's a system on chip builder, and you can kind of think of it just as a library with a bunch of hardware IPs. So it has your processor cores, caches, accelerators, it handles all of the buses, memory simulation, everything. Gives you everything out of the box, as they say, batteries included. And so you basically are always using Chipyard and FireSim together. They can be used separately. You can use FireSim without Chipyard, but it's very difficult. So just use FireSim and Chipyard together to get your designs. So you're using FireSim to simulate the SoC that Chipyard has built for you, and then you're just repeating that process. So now we'll have just a quick overview of the kind of 3 configuration levels that you have access to in FireSim. So at the base level, you have the RTL in Chipyard. This is where you can freely modify existing hardware IPs and implement your own. So make whatever changes you need to do to implement your ideas to do your research. Then the next configuration level up is where you're actually configuring builds. So this allows you to compose a bunch of different IPs together in whichever way you need. So you could have multiple different cores, multiple accelerators, changing the memory hierarchy, changing the caches, compose all of this together, build it. And then after that, after you have this build, then you can configure your simulation. So here you can select workloads to run, and then select which design you're going to simulate and which kind of stats you're going to track while the simulation is running. So going into a bit more detail about these, again, at level 1, you have the RTL. This is where Chipyard is providing you everything out of the box. You can actually simulate an entire SoC without writing any RTL yourself. But if you want, you could modify and add to any part of the SoC. So an example of this, which I'm going to get more to in the demo section, is the paper that I had mentioned at the beginning of this talk. Say you want to have a hardware unit between the cores and shared cache. So this, you have two cores, you have a unit here, and then you have the cache. You can do that. You can write the RTL for it, and then you can hook it up, build it, test it. And we're going to talk about that during the demo. And then going further up again to the build config, you can compose all your IPs together into configuration. For example, you could say, okay, we're going to have two processor cores. We're going to have some hardware accelerator, and then let's also have a shared cache, and then 4 gig DRAM simulation. You can do that. You can also change it. You could remove the DRAM. You could remove the cache. You could have 4 cores, 5 cores, whatever. Configure this how you need, build it. And then once it's time to simulate, you can create different Linux workloads. You can select the hardware design you want to run. You can choose what debug information to track. And then you can go ahead and spin up your simulation with 2 simple commands, and you're good to go. Okay, so that's just like a quick overview of FireSim that we jumped through pretty quickly there. So I'm going to move into the demo section now, which what we're going to do here is I'm going to talk a bit about the file structure first, and then go into just walking through going to RTL, build, and then simulate. So to start using FireSim, the file structure itself is a bit confusing. So that's kind of half the battle is getting into it. So once you're inside of your FireSim directory, there's just a bunch of junk in here. To get to the actual RTL, it's going to be under this target design directory and inside of chipyard, as I discussed in the slides. And once you're in here, you can move into the generators directory. That's where it's going to have all the different hardware IPs. And inside of generators, you can see a bunch of stuff in here. So you can see, I can highlight specifically here, the boom core that is on the bottom left there is an out of order core created by Berkeley. We also have the inside of Rocket chip, there is Rocket core, which is an in order core. We have NVDLA, which is a neural network accelerator. Along with that, we also have Gemini, which is another attached on-chip accelerator. So you have access to all these things inside of here. So specifically though, if we go over here to this editor I have open, and then we're inside target ITL, chipyard again, generators, and then let's go look at the boom core so we can actually look at an out of order core. Scala. Okay, so yeah, you get into generators again, you go to boom, source, main, Scala, and then you are inside of the actual core itself. And then if you open up Colin and go to this config mixins file, what's in here is basically all of these other directories have the actual RTL for the core itself. But then at a top level inside of this directory, you have these config mixins, which basically allows you to create different configurations of the boom cores themselves. So starting here, we have, with n small booms. Basically what this is we can now instantiate any n number of small boom cores, small being a smaller pipeline width. And then as you move up, you can have medium booms increasing the pipeline width, going to large, increasing again, mega, so on and so forth. So you can create these to have just different versions of the same core and all of these different configuration parameters. So for example, you could just modify the fetch width if you wanted to, or modify the number of issue queues you have, just so you can test different things, iterate, and keep moving forward. So that's the boom core. Another thing that I'm going to look at, because that's what's going to be in our simulation today, is under Rocket chip, source main Scala, and then inside of subsystem, it's bandwidth regulator. So this is an example of code you could write yourself. This is the paper I discussed. We actually wrote an entire module to sit between the cores and the shared cache. So again, this is just another Scala chisel RTL file that you write yourself, and then you go and you can actually instantiate it and attach it up into the entire system. And then inside of subsystem along with that, this is kind of where you have your different buses, your memory bus, your periphery bus, your system bus, and other things that you can configure to configure kind of the topology of your entire simulation. Okay, so that's just kind of quickly a bit about the RTL. And then when you're moving up from that level, so you're going from RTL, now we want to go into the build config configuration level. So inside of generators, or not generators, so you have fire chip and source again. Instead of here, you have this target configs Scala file. So this is where you can actually do the build generation where you're composing together all of the different IPs that you have access to. So if I scroll down here to say this one, so it's just, here the naming convention doesn't matter, it's whatever you want to name it, it's just variables in code or classes in code, but here we named it FireSim boom 4-bank config. So basically in here at the bottom, we can see we are using this large boom config, so single large boom. And then these three here are just some boilerplate. You just have to add these in order to use it with FireSim. They're in every config. And then we're also here including an inclusive cache. This is a provided last level cache. It's provided for you. And then we're configuring that to have some number of banks here, in this case 4. And then we're also including that hardware module that I made along with this inside of the FireSim config. So basically what this does is it composes all of these things together. And when it actually goes and builds it, it's just going to include these things. Even though you have all of these other hardware IPs that you may have written out, you can select to only include these ones in the build that you want to run. So how do you actually run those builds if I can find my terminal? So we have this build again, just take note, FireSim 4-bank config, or it could be FireSim 2-bank config, whichever. And to actually go through running these builds, so you'll be inside of the root FireSim directory, and this is where you're getting into the actual FireSim configuration files. Inside of deploy, so inside of deploy, there is going to be a bunch of different YAML files. To start the build process, you want to be inside of the build recipes YAML file. So this is provided for you, and it's kind of after the build configs that we talked about in the target configs, the actual Scala code. This is where you're going to say reference the actual config that you wrote inside of these build configs. So you have just some boilerplate stuff here. The thing we really care about here is this target config. So you can see this FireSim boom 2-bank. We had 4-bank, but this is 2-bank. Same thing, just with 2 banks in the cache. And then we're also including on top of that a DDR3 FCFS model. So this is saying, okay, this is the target config. This is what we want to build. And then the rest of this here is just kind of boilerplate that you're never really going to change. So you have this, you give it whatever name you want. The naming convention here, again, doesn't matter. You can just name it as you wish. And so there, now we've gone from RTL to the build config, and now we're looking at the FireSim configs here. And so now we have our actual full build config complete. So with that, staying inside of deploy, so we have this build recipes file. Now we can go ahead and open up config build, so not build recipes here, we're just opening up build. And inside of here, you'll see a bunch of other stuff, boilerplate, which, when you're actually setting this up locally, which host machine you want to use to do the building, which one's your build farm. The section we really care about here is this builds to run section. So basically down here, all we want to do is we can just reference the build that we actually want to run. And so I have a bunch here I've been using, but basically all of this corresponds directly to the name inside of the build recipes. So you'll just take this name, put it inside of the builds to run section, making sure you only have one uncommented, and then you're set up, you're ready to go. Come back out, and then all you have to do from there is make sure you're in your root FireSim directory and just run one single command. You just do FireSim build bitstream. You run this. I'm not going to run through the whole thing because it takes 4 hours, but this will compile the code, send it over to the build farm, synthesize it, and then it'll give you a bitstream back, and it handles all of the file structuring and everything for you. And to kind of show what you're going to get back from that, if you go into so once you've run the build bitstream, you're going to get this giant log file, which will give you errors and other things if you need to deal with it. But the important part is if it actually completes, you'll get this config build item that has the bitstream itself and then some other things. And basically all you need to do is then just copy this. So you copy this and then bring it into another one of the deploy files. So instead of deploy, there's also config hardware db.yaml. And inside of here, you would then just paste that output from the build inside of this hardware db.yaml. And then you just have this bitstream, and now it's referenced inside of this YAML file. And so now you've gone through the entire build process. So once you have the bitstream and you put it into this build file, then you can actually go to configuring your simulation and running the simulation itself. So to do that, again, you'll be inside of the deploy directory and you'll have this config runtime YAML file. So in here, there is a lot of configuration you can do to actually configure the simulator itself. I'm going to kind of skip around and select a couple different sections just to explain how this works. So the important part that we kind of want to look at is this target config section. In here, you will directly reference that name that you wrote in the build configs. So you can see we have this large boom for 2-bank BRU, what we called it when we actually built it, pasted it in our DB. And this is going to go and reference that bit stream when you want to run the simulation. It'll grab it, spin up the simulation for you with that bit stream. Along with that, in here, you have a bunch of different debug information that you can turn on and off. And then you also have the workloads. It's kind of the more important one. I'll jump back to the debug information. The workloads is where you will specify what workload you want to run, and I'll jump into a second how to build those workloads. But down here, you'll just reference this JSON file, which then when it spins up the simulation, it'll grab the workload for you, spin up the disk image, and it'll all be there running for you with the bitstream on the workload you want to run. For some of the debug information you have, so one of the interesting ones is FireSim has a feature inside of it where it can actually synthesize software assertions into simulation time hardware assertions. So you can do kind of formal verification methods where you're having different hardware assertions in the code, which I can actually show those. If we go into here, So you can write just normal, like you would in C, have these normal asserts, just to assert different states inside of your system. And if you turn on synthesizable asserts when the simulation is actually running, if one of the assertions fires, it'll kill the simulation, print out the information that you requested it to. And that's very useful for debugging and making sure your hardware is actually behaving properly. Another useful one is synthesizable print statements. So along with synthesizable asserts, you can actually synthesize basically C-style printf statements in your code. I can show an example of that from my bandwidth regulator. So yeah, so you can write basically something like this, where it just gives you a C-style printf, and then you wrap it in this synthesized printf. And then if you enable synthesized prints in the build and then in the simulation, during runtime, it'll actually print this out. And you can even wrap it in RTL. So basically say, wrap it in a mux or some other statement and have it only fire out on specific conditions. So that can give you really detailed debug information even while you're working with real hardware. And then there's also tracing. So this is built into every core. If you enable tracing, all it's going to do is just print out every instruction that's executed every cycle. So that's given to you out of the box. So you have a lot of different things you can tweak and use to get the debug information. Okay, so now I'm going to jump into talking about how to actually do the workload building process. That's the last piece we need before we can run a simulation. So that is handled by a tool called FireMarshal, which is again part of FireSim's kind of whole ecosystem. So to get to where it actually is, you'll start in the FireSim directory, and then you need to go to software, FireSim software, boards, FireChip, and then base workloads. So this is where this is going to have kind of all the default stuff in here. So what you have access to in here is a couple different Linux images. You have Fedora, and then you also have a build root image, and then also Ubuntu, which isn't in here. There it is. You also have Ubuntu. So they give you these base images that you can then build off of. Build root's the simplest one to use. It boots the fastest. And basically what you do is you kind of start with this build root base, and then you compose on top of that your files that you want to add into it. So for example, we start with this build root base. We kind of don't need to worry about the file structure, but this just sets up a build root image for you. And then you can reference the build root base inside of your own JSON file. So you give it this workload some sort of name, and then you say, okay, we want to use build root, this build root JSON file as our base of our workload. And then you specify this work dir, which is basically just the directory that you want it to go and look into to grab the files. Inside, I can show in a second, inside of this cache test directory, I have another directory called overlay, and that's the actual file overlay it's going to copy into the disk image. And then you have two other configuration parameters. You can run this host init script, which basically, when it's building the workload, it's going to run this script, and it'll do different configuration things for you. You can just put whatever you want to in there, and it will run it at workload build time. And then guest init is also going to do the same thing, but as it's building the workload, it's going to spin up a VM essentially. And if you do anything inside of guest init, it'll do that inside of the VM, save it, and then when it runs the disk image, you'll have those pre-configured things. So you could have it download packages, you could have it move files around, just set things up for you on this VM before you get to simulation. So it's a bit quicker. So to actually look at what's inside of that catch test directory. So you'll just have another directory, and then you have, again, we have these two guest init, host init scripts. I don't think. So for example, in the host init, I have it actually building some binaries for me. So this will, when the VM spins up, it's going to build the binaries inside the VM. And then when it closes back down and then we go and boot the simulation, those binaries will be there for me. Because doing this build process inside of FireSim itself is going to take a lot longer than if you just do it on a VM on your host. So you can do that in there. And then again, though, we have the overlay directory I talked about. In here, we just have a root directory and then a bunch of files. And whatever you put in here, when you build the workload and then you run the simulation, all of these files are going to be copied over to the simulation for your use. And so specifically, we're going to use some of the files that are inside of this regulation directory, and then also the files from this ISO bench directory. So those are going to have the binaries that we're going to run when we actually spin up our simulation. So we have this, this cache test -build root JSON file that we've made that's composing on top of the build root base. Now we can go back to the root FireSim directory, go into software, FireSim software, and from here you can actually run the FireMarshal scripts or the binaries to actually build the workloads for you. So we can go through that process. So just do .FireMarshal and then just build. Probably get it. The verbose script is nice, or the verbose flag is nice, and then you just directly reference the JSON that you made. So if you run this, and then if you were actually fully building Linux, it would obviously take a lot longer, but this is going through building Linux if you need to, copying over any files you need to, doing all of that for you. And then that's actually built it. And then you have to do one more thing where you have to run the install command. And basically what this does is it just takes the files from the FireMarshal directories, puts it into the correct FireSim directories, so you have access to it when you're actually running the simulation. So now we have gone through the RTL, we've done our configuration there, we've done the build configuration of first configuring our target config with whatever IPs we want to compose together, and then we were in the FireSim directory in the deploy, where you have all your configs. We first configured the config build recipes to actually get your build recipe, say which target config you want to use, and anything you want to compose on top of it. Yeah, you mean?
I need to connect these IPs together. So a way that I want this to be the private chat.
Yeah. So that is just going to be RTL modifications.
Okay.
So for example, I think I'm on the right, I might not be on the right branch to show you that. But so we have this hardware module here, this bandwidth regulator. The way it kind of works in Scala is they have all of these different ways to compose things together. So you have classes, and then on top of that, you have traits that you can then use to extend like base traits. It's kind of like inheritance, essentially. And so, for example, we can have this can have periphery LSE bandwidth regulator. And so when we write inside of our target config with BRU, it's going to, every time it's going to reference this. If we write with BRU, this value, this sum match will be something, and then it'll actually instantiate the regulator itself. And to just give more of an example of where that's actually connected up. So because you want to go between the cores and the private cache, basically you want to connect something up in the interconnect system, and that's kind of handled inside of this has tiles file. So that's where it's actually instantiating each of the tiles and then connecting them with their interrupts and everything that needs to connect to the system bus. So again, just, I know this is kind of hard to follow and a little bit abstract, but just to give you more of an example of how you might do this. Basically in this has tiles, it's going to go through and connect everything. And so you can just, what I did to get this to work is just jump in the middle and reference that LLC BRU. And then you change a bunch of other things. Again, it's just RTL configuration at that point. You are just, I can show you actually where it's used, just to show. So basically you have this BRU node, and then what these symbols here are the actual hardware connections. So you would basically just, and before it was just, you'd have the core, and then you'd have the system bus or whatever. You just then interpose the BRU or whatever right in the middle, put the connections on either side, and it's handled for you. I don't want to go too deep into the details of that, but there is this whole thing around the actual modules where there's two separate parts of the modules. There's the actual hardware RTL, and then there's this whole other configuration portion that handles all of the connections. So you're kind of just messing with these two different things to get that to work. Yeah. And so since I have all of this, again, then once you go back to the target configs, once you instantiate this, it'll actually give you something and it'll connect it up. If it's nothing, then the compiler, the FireSim compiler, the Golden Gate compiler has a way to just throw it out and ignore it. Yeah, so we have that IP, we have modified this, the build recipes, we built it, we put it in the hardware DB, and then we modified our config runtime. We built this workload. We're specifying we can use this workload, and then we're specifying that we want to use this specific hardware config that we've built. So from there, we can actually go to running a real simulation. So to do that, again, so this is actually using, so that picture I showed you with the FPGA on it. So this is actually SSH into that machine, and we're going to run a simulation on that FPGA. So first, you have to do this infra setup command. So this is just going to move all of the simulation files over to the simulation machine. It's going to flash the FPGA. And then once that's done, we can actually run the simulation. So this takes a few seconds to do. So does anyone have any questions while I'm waiting for this to finish? So like the way we have this set up in our lab. So this manager instance would be my personal machine. And then the build farm is a separate machine, the Moonstone machine, which has a very, it's when you're setting up a build farm, it's important for it to have really high single threaded performance. That's Vivado synthesis is kind of multi-threaded, but it's like 5, and it's mostly single threaded performance. And then the run farm is that picture I showed where we have the actual FPGA hooked up to it. So if you were setting this up, you'd have your manager instance would be your machine, and then you would use the build farm and the run farm as we have it set up. Flash. It's actually side of shipyard. So we talked about the boom core. That's what we're actually going to be simulating right now. You also have access to a bunch of other cores, one of them being the rocket core. So let's see, side of here that's inside of a rocket core, that's going to be an in order version for you to use. along with that, I forget exactly where they are file structure, but there is other cores to use. You can actually even you don't have to write everything in Chisel. You can write Verilog and then use this method they have in Chisel called Verilog blackboxing, where you just basically set up the inputs and outputs and then wrap the Verilog, you reference a Verilog module and just wrap it. And then once the Verilog from the Chisel is produced, it just slides the Verilog in. And so you can use Verilog modules inside of Chisel modules. So an example of that is the MVDLA is a Verilog black box. And there's also a core in here. I'm not sure if it's the IBEX core. I think it might be. Yeah. Yeah. So you can see this file here. This is an entire core that's a Verilog black box. So yeah, it's possible to do. Of course, you have to deal with looking up everything. It's a bit tricky, but it's an option.
I think that one changes input configuration of the core.
Yes, yeah, that's where I was talking about where it's a bit difficult to iterate with FireSim. Because every time you have to build. Now, there is one, after I get through this simulation, there is one way you can kind of test those things through meta simulation. But yes, I'll talk about that here in a second. Okay, so since our, again, we ran FireSim and for setup, so that set up the infrastructure for us, and then we can just do run workload. So we can just, once you have everything, just 2 commands, and it's going to go ahead and spin up the simulation for us. So we can just see some stats about it running here on the left, just seeing that it's live and how many instances we have running. For us, we have only 1 FPGA, so there's nothing running. But if you had a AWS going with 10 FPGAs, it would tell you, okay, we've still got 10 running, or hey, one of them's finished, and you can check the individual stats of each one. So then on the right here, I'm actually SSH'd into the machine with the FPGA on it. So we can go ahead and just start a screen session or restart the screen session because it already started one for you. And then we are inside of the simulation itself. And I'm actually going to come out of it for a second just to look at what happened there. So we can actually see here like OpenSBI and Linux actually booting on this hardware that we got simulated in real time.
We can interact with this.
Yes, and that's what we're going to do right now. So we're literally at a Linux login. We can go ahead and log in. And now we are interacting real time with the simulation itself. And so we had talked about, we had implemented this kind of unit, bring up the slides again just to show it, this unit that sits between the cores and this cache. So all this unit does is just going to allow us to regulate bandwidth traffic. So if we want to say the core can only do 50 megabytes a second, we can do that. So that's what we're actually simulating right now. We're not simulating a dual core system, we're simulating a single core system. And again, since we're using Linux, I can actually show you that. We can just cat proc CPU info, and there we got a processor that's available to us and that we can see. So first we can just try running some workloads. Ignore that. And so all I'm going to do here is just run a simple workload that just sends a bunch of memory traffic to the caches. So you just run it here on core 0 for a second and use 250 kilobytes worth of memory. And it's going to go ahead and run. And once it completes, we'll see the actual bandwidth that it got. And again, this is real hardware, so it's representative of what would really happen if you taped out this chip. So there we go. We got 6.6 gigabytes out of our LLC. So that's, if you're just using ChipYard, you're going to get performance like this. But let's go ahead and actually interact with the unit that we implemented for the paper I mentioned. So we'll just go ahead and set up regulation. So basically what I'm saying here is don't worry about the numbers, but I'm basically just saying, let's limit this to 320 megabytes a second. And then we'll go ahead and run a different workload. Workload that's sending traffic to the LLC. So in this case, if you remember in our configurations, we had said that specifically the one we're using, we want to have 2 banks in our last level cache. Here, what I'm going to do is I'm just going to, and for this, we had said, okay, let's go ahead and regulate the access to those banks at 320 megabytes a second. And then I'm running a workload that's just going to target a single one of those cache banks. So we can run it. Yeah, so we run it, sets everything up, runs the workload, and there we go. We get around 320 megabytes a second, the regulation value that we set. And then if we go ahead and give it access to both banks, since we're regulating 320 per bank, we go ahead and give it both banks. Now it's not double because of some performance issues, but it's higher than if you were just targeting a single bank. So this is us interacting with the actual hardware IP that we implemented, built, and are now simulating.
What was that script that you were on bridge?
Oh, that was just, it's not important. It's just a binary I have to write to some memory mapped registers.
Okay.
Yeah, that's all. It's just for configuration of the hardware IP. Yeah. Let's see. So yeah, that's again, we have this real simulation that we can interact with in real time. If you're using Gem 5, you can't do this live. Gem 5, you set everything up and run, and it'll finish in a day. And hopefully it worked. So then you can actually shut it down just like a normal Linux machine, and it will turn off the simulation for you. And that's kind of the whole flow of doing real architecture simulation with FireSim. Out of the box, it's really pretty simple. You just set up those configs and then run it, and you're off to the races, and then you can start modifying RTL as you need. Now, to Amin's point, if you are wanting to say, do a design space exploration and modify something 10 different ways, you have to build 10-bit streams. That's kind of the downside of using FireSim. If you're testing something, though, there's another method of simulation called meta simulation. And basically what that is kind of what it sounds like. It simulates the simulator. So it'll take this entire FireSim simulation infrastructure, turn it into C++ code, and then run it through a tool called, well, I guess it turns it into Verilog, and then it runs it through a tool called Verilator, which takes Verilog to a C++ simulation. Then you can compile that and run that. You get back to the issues of software simulation with that. It's going to run slower than the FPGA accelerated simulator. You can't really run an OS on it, but it's useful for testing basic functionality of new IPs that you might implement. So we can actually, I think I should be able to just spin one of those up. So to do that, you'll be, again, inside of that config runtime, that simulation config file. And at the top, there's this whole section for meta simulation. By default, it's set to false. Actually, I might not be able to spin this up right now because it has to build it, and that takes a while. But basically what you would do, set that to true. You can select Verilator here. You can also use VCS, but that is a paid tool. It's not open source, so we can just use Verilator. And by setting it up, just by changing this value to true, what's going to happen then is when you go to do your FireSim infra setup, now what it's actually going to do is it will go through, and this is going to be weird because I'm on a bunch of different branches, but it'll go through and actually compile the whole hardware setup that you have that you want to run, and then run it through Verilator and get you that actual C++ simulation model out on the other end. This would take too long to do live right now, but Then when you run it, again, you run it the same way you've done for setup, then you would just run FireSim, run workload, and it would give you the same access over on the simulation host. So you can just access it like you would normally do with the screen terminal, and then interact with it. It's slower, but you can still interact with it. But typically the way you're going to actually do it is run like a bare metal workload on it and have Fire Marshal set up in a way just to run it automatically to test whatever you might want to test. And since you're using the software simulation, the build itself is a lot faster. It doesn't take hours, it takes 2 minutes. And then you can, have just normal print statements in the code, do different things to kind of debug things a little bit quicker. But it's trickier at that point. It's trickier to work with than just using Gem 5, in my opinion. So that's kind of where you get the trade-off of you have faster simulation times, but at the cost of longer build times. And that's why it's harder to prototype things out in FireSim, as you've seen. So, yeah. So, thought I would, but do you have any other questions? Well, I guess, be, even though I'm writing RTL here, if you look at this code, it's a lot of it looks, like this doesn't look like Verilog, right? This is normal object-oriented functional code. So if you take a class in Haskell, Scala is a lot easier to look at. If you learn C++ and know object-oriented programming, Scala is a lot easier to work with. Chisel I learned on my own, obviously, but those skills I learned in undergrad were very helpful here. Obviously, all of my architecture knowledge from my undergrad courses, I needed that for this. I mean, I took an advanced architecture course in my graduate I needed that to do this, but a lot of what I learned in undergrad was, I use it all the time when I'm, yeah. It's not like I learned anything. It's all indirectly related, I guess I would say. It all, as is everything, it builds on itself. So if you didn't have the undergrad time spent learning all these things, this would be much harder to learn. Yeah. So a previous student in my lab had used it 3-4 years ago. And then when I came on, we wanted to use it again because along with the speed benefits in the real-time systems community, in systems in general, people really like real implementations, real hardware. It's a little bit harder to get people to buy Gem 5 in our community. But when we can say, hey, we can actually take this out on a chip, here's how much area it actually takes up. Because you can do area analysis in Gem 5, but again, it's not as accurate. So that's why we choose to use FireSims, because it's just more beneficial for our community. People like it more, and it's more relatable to what people are actually doing in industry because it's real hardware. They say that industry has used it. Not to rag on Berkeley, but they have their whole infrastructure, and then they have Sci5, which is basically Berkeley. So they can say industry uses it, but maybe just Sci5 uses it. I doubt anyone's actually using it really in industry because if people were using it, I wouldn't have as many problems with it as I do, because it's still a research tool. But I still think that learning how to use something like this is transferable to industry because people do similar to this. They do FPGA prototyping, which, while not exactly the same, you're still using an FPGA, you're building out this whole SoC, so it's transferable skills.
Usually they have their own in-house simulator.
Yeah, everyone's got their own in-house simulators typically. So, and they're proprietary and they don't share them, so, yeah. Okay, well, yeah, I guess if no one else has any questions, that's all I got. I went through that faster than I thought I would, but. Yeah, yeah, of course. Learned something. Well, and Berkeley uses this in their undergraduate courses. Yeah, they use Chipyard to teach computer architecture. At least they used to. I know they flip flop back and forth on whether they should use it because it's in Chisel or whether they should use something in Verilog because that's more relatable to industry. But you can look online and their course syllabuses have FireSim and Chipyard where, and it's really nice because they can set up environments where it's like, okay, an inner processor is really abstract, but okay, let's set up a simple configuration for them to go and access and say, okay, what happens when you add another pipeline stage, or if you change the number of registers, how do your stats change? So it can be used for educational purposes, just with some extra tweaking. Yeah.
Sounds cool. I think it ended up like taping out a chip or something like.
Yeah. I mean, that's the other really cool thing is the fact that you could do all this research work and then you could actually tape out a chip at the end of the day, which I think would also be cool for an undergrad to be able to go through the whole flow and then, see see this at the end of it. Be like, oh, hey, this is the processors I configured, and like that's literally what it would lay out like if I actually put it into production. So very useful for research, obviously, to ground our results, but also for undergrad courses, even graduate courses, it could be